Okay, well, I guess that looks like it's recording. That's a little weird, but anyway, here we go. So last time we were talking about linear approximations, and let's see here. So linear approximation. Now we assumed, and we kind of made an asterisk, and so we'll come back and deal with this later. But we're assuming that the linear approximation actually exists. And on the assumption that it exists, we figure, well, it's got to have certain features, and therefore, there's only one function it could be. But all of the thing that we did was, in fact, assuming that it actually exists in the first place. Can't assume that, really. We are going to have to come back and fix that, and we'll do that in a few minutes. But just a reminder, what we did is we argued by analogy from how single-variable linear approximations work. And for multivariable, although, we're going to start by considering just real-valued multivariable, this is the formula that we ended up with. So basically the gradient plays the role of the derivative, at least in this circumstance. And then we saw an example, numerical example here. Okay, so that's where we ran out of time. So now we're going to go on and consider what happens in the vector-valued case. So suppose that we had, so this is our kind of most general category of function we're going to talk about. Multiple input variables, multiple output variables, right? And how do we deal with it? Recall that the gradient here, the gradient was a notational convenience, right? It saved us from having to write all this ... stuff over here. It's a little ugly looking, and plus, dot products are natural, and x minus a is natural, and so this is not really quite just only a notational convenience. This is also kind of verging toward writing things down in a way that is fundamentally natural. But anyway, initially, our motivation is that this is a notational convenience. So rather than write down the ugly formula and then write the notational convenience after, I'm just going to start with the notational convenience, because writing this all out, all the terms, would really be, it'd be a lot, and I don't want to waste the space for it. So here's this new construction. Again, I'm going to kind of pull this out of thin air. We'll see later why it's useful, but we're going to define this thing called df, and it's this matrix right here. Notice it has something in common with the gradient in that it's made up of a bunch of partial derivatives, right? Arranged in a certain way, not as a vector, but as a matrix. Okay. And then further, notice how these partial derivatives are arranged is there's a pattern to it. Notice, for example, in this first column, all of the partial derivatives are all partials with respect to x1. So that said, I'm going to call this usually the x1 column, because that's where the x1 partials all go. Okay. Then you'll notice ditto for the x2 column, x3 column, etc. And then finally, lastly, the xn column, all the partials with respect to xn. Okay. Now, furthermore, though, notice that the rows also have all of the elements in any given row all have a common feature. They're all partial derivatives of the same output coordinate, right? So in the top row, that first row, those are all partials of f1. So one could reasonably call this row the f1 row. And then likewise on down the line. So one way to remember this, this is just the way I think about it, but columns correspond to input variables. Rows correspond to output variables. For your consideration. By the way, the specifics of how the elements in this matrix are arranged is important, and it is easy to get backwards. It's easy to accidentally transpose this matrix. If you have the columns correspond to output variables instead of input variables, then you've transposed your matrix, and everything is going to be wrong, and everything that derives from it is also going to be wrong. It's a catastrophe. So please do be very careful and notice which way it goes. Columns correspond to input variables. Rows correspond, colors. rows correspond to output variables. Okay. All right. Now, with that notation set up, here's our linear approximation for vector-valued multivariable functions. And notice it looks an awful lot like our previous linear approximations. Constant term plus something times x minus a. Structurally, it looks just like the previous formulas. The difference is that, of course, now this is a matrix that we're multiplying by x minus a. It's not just a vector that we're dotting with x minus a. Now, when I say that this is the linear approximation, I mean that in the same sense that we did on the previous page. Namely, this is the unique first-order polynomial that agrees with f in value at a, and it also agrees with f in all of the partial derivatives at a. I'll just do it like that. And when I say all the partial derivatives now, you got to keep in mind there's a bunch of partial derivatives because there's a bunch of different input variables with respect to which I could take a partial derivative, and there's a bunch of output variables of which I could take a partial derivative. So, yeah, that's a bunch of partial derivatives to check. Now, again, just like the previous cases, I think it's a healthy exercise to confirm this for yourself. Doing this calculation here will be a lot like what we did on the previous page. So, I'm not going to go through it here, but I think y'all should take a crack at it. Don't try to do this in general for, n by m. There's just too many, it's too notation heavy. So what I'm going to suggest is that you do it for 3 by 3, right? Just keep it to 3. And with a 3 by 3 matrix, namely 3 variables in, 3 variables out, you've got a relatively short list of terms. You can write down all of the terms. You could literally write down all 9 terms that show up when you do this multiplication. Right? And you can take the corresponding partials and confirm that they are what they're supposed to be. So again, healthy exercise. If you get stuck on that, come to office hours. We'll clean it up. We'll talk about it. We'll make sense out of it. And of course, you're also welcome at the other instructor office hours. You're also welcome in the help room, whichever works best for you. Okay, example. Here we have a vector-valued multivariable function. Right? And let's make the linear approximation, in particular at this point here, 1, 2. And I'm just going to work directly from the formula we just talked about. There it is. So, alrighty, the first thing I'm going to need apparently is f of a. So I'm going to take this point a, plug it into that function f, and there you go. There's f of a. That's the easy part. You just plug it in. Okay. All right. Next. Apparently, we're going to need to know this thing df, specifically df at the point A. All right. Well, to find the general df matrix, we're going to take a bunch of partial derivatives. Now, that's just like what we have up here. Arrange the partials in this proper order. So, as pertains to down here, notice this entire first column or the partials with respect to the first input variable. Remember, columns correspond to input variables. So this is all the x partials. Boom, boom, and boom. Right? And then the second column is all of the partials with respect to the second input variable. And again, that's just partial derivatives, so that's easy to compute. So that gives us our df matrix. Of course, we've got to plug in the point A. So we plug that in there. Plug in 1, 2. So x is 1, y is 2. Plug in the numbers, do the arithmetic, and you get that the derivative matrix at the point in question is this matrix of those numbers right there. So, making progress, right? We've got our first term, we've got the first factor of our second term, and then lastly, x minus a, and this is, y'all have seen this before. X minus a is easy to see because x is x comma y. Those are the input variables. A is the point where we're doing the evaluation. That's 1, 2. And so you subtract and you get this vector here. So there you go. And again, you could multiply this out, I suppose. I don't really see particularly why we should feel the need to do so. In fact, some significant amount of convenience and information is lost if you multiply this out. Most of the time, I don't really see the point. Okay. All right. Is everybody on board? Okay, we've already made these observations, but again, the columns are all the partials with respect to the corresponding input variables. And then just a neat observation here, though, if you look at the rows, let's go back up here and actually see it. Here's our DF matrix. A row, we've already noted that that's all the partials of that one coordinate function. Where have we heard that phrase before? All of the different partials of a given function. That's the gradient. Now, of course, the gradient is a vector, so it's written vertically, typically, or comma. Comma means new line, of course, right? So this is actually a vertical vector, just, for typographical convenience, it's written horizontally. But it's actually a vertical vector. The derivative matrix has them arranged horizontally. So there is that little difference, but it's all the same entries. Is that cool? Okay. Again, reminder, let's be quick about this. I mean, technically the linear approximation is not linear. It's something called affine. You don't need to worry about that. DF, though, being as it is a matrix, matrices are linear transformations. So this is why they call it a linear approximation, is because most of the heavy lifting being done by the formula is being done, of course, by that matrix, and that matrix is linear. Okay. All right. So, moving along. Flashback to single variable calculus again. I hope you all remember tangent lines. And recall that a tangent line is closely connected to a linear approximation. Again, in high school, very often these are conflated. And this is a problem. I shouldn't say high school. In single variable calculus, the tangent line and the linear approximation are very often conflated. We have to be more careful than that here. The connection that is usually swept under the rug is that these are connected by way of the graph construction. Specifically, the tangent line is the graph of the linear approximation. A line is a geometric object, after all. A linear approximation is a function. It's an algebraic object. They are fundamentally different things, right? So, yes, they're related, but they're related in a very specific way, namely the graph. And you can see that in the way we have this written down here. Here's my linear approximation, right? Or a formula from the couple pages back. There's our linear approximation. The tangent line is what you get when you take the graph. When you set that function equal to this new variable y, that gives you the tangent line that you can draw a picture of. Okay. All right, so that's just cleaning up some old stuff, but notice now we can apply this exact same idea in a higher dimensional context. Suppose we have a function of two input variables now, and we can make the exact same statements. We have on the one hand, this is our linear approximation. All right, real valued function of two variables, so we're going to use this gradient formula. All right, linear approximation. And if we take its graph, namely if we set its values equal to a new variable z, then the result of taking that graph is the equation of a plane. And that's what we call the tangent plane. In the same way that the graph of the linear approximation in the single variable case is the tangent line. Okay, so highly analogous. What do you think? Everybody okay? Okay, now on to some difficult, uncomfortable realities that we're mostly going to skip. But I got to go back to this question here. So, we found the formula for a linear approximation by assuming that it exists, and then based on, I feel like it should have certain features, therefore it must be this thing, I suppose, right? But that was all assuming that it exists in the first place. So how do we know that there really is a good linear approximation? What does it even mean to be a good linear approximation? What features must a function have to be called truly a linear approximation? So this is a deep question. And a full answer to that is far more than we can or should talk about in Math 219. So again, we're not going to get super rigorous about this, but I want you all to see some examples of the kinds of issues that can come up and the kinds of tools that you might use to address those examples, and then we'll wrap it up in a bow at the end. But we're going to start off with this function right here. This is an admittedly weird function. It's defined in chunks. So everywhere except where one of the coordinates is 0, the value of the function is 0. So for example, out here in the first quadrant off of the axes, over here in the second quadrant off of the axes, ditto third quadrant, ditto fourth quadrant. As long as you're off the axes, the value of the function is 0. But then now, notice if we're on either axis, right? If either x or y is 0, well, for those cases, the value of the function is 1, which means that the graph for those points is way up here. Right, giving us, for example, this is the part of the graph above the x-axis, and then likewise here, I'm not going to draw all those, you get the idea, is the part of the graph above the y-axis. So it's kind of like the graph is what you get by taking the xy plane and just literally lifting up the x and y axes themselves by a distance of 1. This is a pretty weird picture, but anyway, that's what the graph of this is. Okay, let's talk linear approximation. Question.
Could you use the delta epsilon proof to?
Oh yeah, but see, delta epsilons is how you treat limits, and you may recall we skipped the section on limits. So yeah, no, you're right. There is a delta epsilon approach to all of this, and that's well beyond what we need to worry about.
But like, if you did it in multi-variable, would you make it a sphere?
Make it a what now?
Like a sphere.
Yeah, that's right. I mean, right. So I'm going to give you a very short answer and then offer to talk to you after class if you're interested, because it's pretty far afield. But yes, the way you use epsilons and deltas to define limits in a multivariable context is to use those epsilons and deltas to define little balls. Yeah, that's right. Instead of intervals like it is in single variable. Yeah, absolutely. Yeah. Feel free to talk to me after class. Happy to elaborate. Okay, so let's pretend that the linear approximation exists naively, right, and see what we get. And recall our formula for the linear approximation is, here it is. Here it is. There's our formula. So as long as I know the value of the function at the origin, where I'm going to do the approximation, as long as I know the gradient, namely as long as I know the partial derivatives, I can just write this down. And here we go. What is the value of the function at the origin? Well, at the origin, the value of the function is 1. Because both x and y are 0. Not only one of them is, but both of them are. Okay, what are the partial derivatives? If I'm at the origin, right, and if I start moving, for example, in the x direction, as I move in the x direction, how does the value of the function, which we agreed is 1, how does that value change as I move in the x direction? And you'll notice here from the picture, it doesn't change. So the partial with respect to x is 0. No problem. At the origin now. Right? There's definitely problems elsewhere. But at the origin, in the x direction, it's just flat. And then likewise, if I ask, suppose I start moving in the y direction in the interest of computing the y partial. How does the value of the function change as I go that way? Well, again, it doesn't change at all. Constant, it's 1. So that partial derivative also perfectly well defined, also 0. And if you write down the formula from several pages back, where this is the f of a, and then here's your partials, there's the whole gradient term goes away because it's all zeros, and your linear approximation is just this function 1. Here, let me make a different color choice here. The linear approximation is this function that's just flat 1. Let's see here. I'll bet you I can. There we go. Okay, so this is the what you might call the tangent plane that you get by looking at the origin. Now, is that a good linear approximation of this function? I say no. Check out what happens if you approach the origin. Here, keep in mind, there's the origin. If you approach the origin from inside of the first quadrant like this, the actual value of the function is 0 all the way along there. The value of the linear approximation, as you're doing that, value of the linear approximation is 1 for all of those values. So how far are you off? What's your error as you approach the origin along those lines? Your error is always 1. Your error doesn't approach 0. How good of an approximation is it if your error doesn't even approach 0? I mean, that's not good, right? So this is what I'm going to call a clear failure. The formula we wrote down previously claims to give a linear approximation, and obviously we need to reject this. Now, how do we reject it? I'm going to observe that this error that I've drawn a picture here of, I can just write down the formula. It's F minus L, actual value minus approximated value. And I can just say, look, I feel like the error should have to go to 0. And this didn't, so not cool. Everybody with me? All right, now, next question. Is this good enough? This requirement, can I just say, look, I just need the error to approach 0 and that's going to solve all my problems? Actually, it doesn't. Tragically, look at this example. Here's a function, 5x. Here is a candidate linear approximation, right? This function shows up and says, hey, I think I'm a good linear approximation of your function f. How do we reject this? Can we reject it by claiming the error doesn't approach 0? Nope. Tragically, you look at the error here. The error, I can draw a picture of it. There it is. There's the error. And as I get closer and closer to the origin, that error indeed does actually approach 0. So claiming, let me say this, requiring only that the error should approach 0 does not eliminate this in its claim to be a good linear approximation of that function. And again, let's just take a look at this thing. Is this blue function doing a good job of approximating that green function? No, clearly not. This is terrible. The actual linear approximation of this green function f is just f, of course. It's an easy example, right? So this is just heading in the wrong direction. This is a bad linear approximation. We need our requirements for linear approximations to reject this. And requiring that the error be 0 doesn't cut it. Okay, so we need to refine this idea. The big idea to do this is to define a new concept called relative error. Relative error is actual error divided by x minus a, divided by, so it's how far off is your estimate of the output divided by how far away are you from the input where you're doing the linear approximation. Right? So this ratio, this is what we call the relative error. And let's use relative error now. Let's require that relative error approach 0 and see what happens with that last example where error itself kind of failed. It didn't do what we needed to do. So, okay, here we go again. We got this function here, 5x. We got this function here, 3x, that wants to claim that it's a good linear approximation. Let's look at the relative error. Keep in mind, relative error is error. Sorry, I wanted to be in pencil mode. Error divided by how far away we are in the domain. And that error is easy to write down. The error is just the difference of those two functions. How far we are away in the domain, x minus a, we're doing the approximation at 0, so that's just x. This is an easy limit to compute. And so this relative error does not approach 0. So this candidate, this very poor candidate to be a linear approximation to f, has failed this test. As it should. Of course it should. It's a terrible linear approximation. Right? So what we've got then is a good criterion. This idea that we want relative error to approach 0 correctly rejects this bad candidate in the way that error alone did not do. Okay, so we're going to model our definition of differentiability, our definition of what we mean by a linear approximation on this idea of relative error. Defined like so, we need relative error to approach 0 as x approaches a. And don't forget now, of course, this error thing right here is value of the function minus the value of the approximation. Further, don't forget the linear approximation is this formula right here. And now just for transparency, I'm going to put some parentheses. Oh, you know what? That looks too much like the black. Let me... let's see here. Let me use... Actually, blue works pretty well. Right, distribute the minus sign and all that. So when I say relative error, put the pieces together, and this big monstrosity here is relative error. All of this together, and if you look up the definition of differentiability in the book or anywhere else, you're going to see that the requirement to be differentiable is that this monstrosity has to approach 0 in the limit as x approaches a. And where it comes from is that all of this is just a fancy way of saying relative error. How far off are you in the output divided by how far are you away in the input. Okay. All right. So, so to our original question, under what circumstances, when we write down our usual formula for the linear approximation, under what circumstances is that actually a legit linear approximation? The answer is that function has to be differentiable, namely relative error has to approach 0. All right. Which, sadly, is a hard thing to work with because look at the size of this monstrosity. We don't want to have to deal with that. Further, notice, we kind of skipped the section on multivariable limits, and so we don't really know how to do this either, right? So function, as a, working mathematician's definition, this is going to be a hard thing for us to work with. We're not really prepared to work with this. So what we need is something a little bit more user-friendly. Before I get to that, I want to say a couple of quick words about language. Of course, we've thought of this thing here as being the actual value of the function minus the approximated value of the function. But I'm going to kind of move things around a little bit now and reinterpret this as the actual change in the value of the function between x and a. This is what we call the increment. How much the actual function actually changes. Increment. Minus how much our linear estimate changed between x and a. And this formula right here, this is the part that measures how much, based on the linear approximation, how much we estimate the function changed. This, again, standard term, this is called a differential. And you may recall this term from single variable calculus class. Differentials are linear estimates of change. So there you go. So increment and differential, make sure to remember the difference. It's an important distinction. Okay, so back to the ugly reality. Do I actually have to deal with this monstrosity and the ensuing multivariable limit? Oh, gosh, it's looking bad at this point. Good news? No. There's a wonderful little workaround. The workaround is called continuous differentiability. This is a new idea. It is not the same as differentiability. This is a more sophisticated construction in a way. It's a stronger constraint. It's a stronger condition. So here's the definition. It's exactly what you would hope it would be. It's actually a very simple definition. Continuously differentiable means look at the partial derivatives, confirm that they exist. Sometimes functions are undefined in some places, right? So make sure nothing explodes, right? And then make sure that they're continuous. That's it. Now it's seemingly an arbitrary definition, right? But you got to give me one thing. It's really easy to check if a function's continuously differentiable. Partial derivatives are the world's easiest derivatives. Checking to see if something explodes. It's just look. Did I divide by 0 somewhere? Am I taking a tangent of pi over 2 somewhere? Right? Just look and see if something bad happens. And then for continuity, look to see, as will probably be the case, is each one of these partial derivatives in one of these large categories that we know the functions are always continuous. Polynomials, for example, all continuous. Exponentials, compositions of exponentials and polynomials, all continuous. Trig functions, logs, are all continuous where they're defined. Now this is, of course, obviously, like tangent fails to be defined in certain places, right? But where it is defined, continuous. So eyeball, easy to confirm when a function exists and is continuous. And so, all right, so yeah, but what can we do with it? We've made a convenient definition here. Well, how does this help me with differentiability? The way it helps us is this easy-to-check condition that we kind of just made up. Any such function, always differentiable. Right? The thing that I would have to check with that monstrosity on the previous page. Immediate conclusion from checking continuous differentiability. So that's a pretty sweet deal, right? It's really nice if you can. Don't deal with all of this nightmare. Just check that it's continuously differentiable, and if it is, free answer, your function is differentiable. Let's see an example. Here's a function. Is that function differentiable, we ask. All right, so am I going to go at it with the monstrosity? No, of course not. We're going to try and hope that this function's continuously differentiable. So I take the partial derivatives. In fact, I tell you what, I don't even have to take the partial derivatives. I know that the partial derivatives are all going to be polynomials. I don't really need to know exactly which polynomials because I know that all polynomials are continuous. So our partial derivatives are continuous, so this function is continuously differentiable by definition. And once you know that it's continuously differentiable, it's differentiable. Game over. No monstrosities. Everybody on board? All right. Okay, so in practice, day in and day out, this is tends to be how we most of the time confirm differentiability. Okay, here's another useful fact. If a function's differentiable, then that implies that it's continuous. Now, how is this useful to identifying differentiability? The arrow is going the wrong way. Sadly, the arrow does not work the other way. So, as written, it doesn't look particularly helpful for me deciding whether a function's differentiable or not. I'd have to know the answer in order to be able to apply this implication, and the result would not be about differentiability. So it's just backwards. So to be useful, so I'm going to use a construction called the contrapositive. The contrapositive is basically if you turn the arrow around backwards and put not in front of both of those statements. And as it turns out, the contrapositive is equivalent to the original statement. So here we go. Let me walk through what I mean by this. Let's suppose that we have a function that's not continuous. Let's just say, hypothetically, I have a function that's not continuous. Now I ask, this function that's not continuous, is there any way it could be differentiable? Well, the thing is, if the function is differentiable, that would mean that it's continuous, which we know it isn't. So there's no way that this function that's not continuous, there's no way it could be differentiable. That would create a contradiction. So if it can't be differentiable, then that means that it is not differentiable. So anyway, it's a clever little logical move. It's called the contrapositive, and this is the one that we're actually going to be able to make use of. Notice the test does not assume that I know the answer to the differentiability question, and note that the result gives me an answer to the differentiability question. So anytime you see that a function fails to be continuous, you're all set. That function couldn't possibly be differentiable. And so, for example, this weirdo right here, right, that we talked about, that function has a discontinuity at the origin. It has a pretty nasty discontinuity, right? Big jump discontinuity or whatever you want to call it. So, not continuous, and therefore, it's not differentiable. Everybody with me? Yep. Is it what now? Yeah. I'm not saying it's not defined. The value of the function at the origin. The value of the function at the origin. You're quite right. The value of the function is 1. But continuity, in some sense, means, and I don't want to get off into the rigors, but it means that the graph looks nice and sort of connected, and it's a smooth looking kind of thing. And this graph isn't. If I look in the vicinity of the origin, right, for some of these points, the value of the function is 0. For all these points over here, the value of the function is 0. And then the very moment that we get to the origin, all of a sudden the value of the function is way up here is 1. And so there's a kind of a jump discontinuity there. Does that make sense? Yeah. Right. Okay. All right. Okay, the next couple of pages here are largely terminology. But the terminology comes about from rephrasing stuff that we've seen. And I think this specific rephrasing, or this specific sort of reformulating, is actually a really important tool in understanding this thing called DF that we've been using to form linear approximations. So here we go. Let me start the rephrasing. Here is our general, vector-valued, multivariable linear approximation formula. And now I'm going to observe, one of the rules for a linear approximation is that it has to agree in value with the function it's approximating at the point where you're approximating it. So L of A has to equal to F of A. That's one of the rules. So I can rewrite F of A as L of A, and having done that, if I take this and move it to the other side of the equation, notice that the equation now turns into the left side being exactly the output differential, and the right side, of course, now if I look just at this factor from the right side, that factor on the right side is the input differential. So input change and output change. And you may recall one of the very first things that I said about derivatives, right? And I pointed out we're going to have a bunch of different kinds of derivatives in this class. Why don't we go ahead and take stock real quick while we're here. We've seen partial derivatives. We've seen the gradient, which in certain contexts kind of plays the role of a derivative. And we've seen this thing called df, which in a different context kind of plays the role of the derivative. Well, now I've got this phrased to explicitly fit the sort of the point of view that we started this section with, namely, df is the thing that relates input changes to output changes. That was our defining characteristic for the derivative. Right? It turns input changes into output changes. So, typically, this is what is referred to as the derivative. Now, again, there's a bunch of different derivatives, so sometimes we clarify and call it the derivative matrix. Just to clarify, yeah, I'm talking about the matrix one. Yes, there's a bunch of different kinds of derivatives, but we mean the matrix one. Don't forget all matrices are linear transformations, so sometimes this is called the derivative transformation. And in this class, we're not going to sweat the distinction between linear transformations and matrices. As far as we're concerned, they're kind of the same thing. You know what I mean? So either of these terms is fine, but importantly, this is the thing that does, in general, what derivatives are supposed to do. This is the thing that you do to input changes to get output changes. And in the most general sense, any number of input variables, any number of output variables. So you may also recall, like 3 minutes after I pointed out that there's going to be a bunch of different kinds of derivatives, and we started defining partial derivatives, and I gave you this disclaimer of, hey, don't hang your hat on this concept of partial derivatives. Because partial derivatives, they're a nice, convenient first step, but they're ultimately not really how you should think about derivatives. And if you leave this class with, a fundamental point of view on what derivatives are, it should be not partial derivatives, but it should be this one. This is what a derivative really is. A derivative is this matrix. What do you think? Everybody okay with that? All right. It is, by the way, I want to acknowledge it's a little bit weird and sort of counterintuitive because we went through, we have all in our own times gone through single variable calculus classes, and if you have a function and you take the derivative and you plug in some input value, the answer is always a number. And so you may kind of, have it in your head that derivatives are numbers. And, well, importantly here, they're not. Derivatives here are matrices for what it has to do, right? I mean, if you're going to turn input changes into output changes, those input changes are vectors. Those output changes, also vectors, right? And matrices in general are the things that turn vectors into other vectors. Okay. All right, enough of that. Oh, another little terminology thing. Sometimes this is called the Jacobian matrix, and when it's called the Jacobian matrix, it's also sometimes written as JF. So a little terminology and notation to be on the lookout for. In this class, I'm going to try to use the term DF, but that said, I will sometimes say Jacobian, because when I took multivariable calculus, however long ago that was, my teacher always called it the Jacobian matrix. So anyway, I've got some of that drilled into me. Okay. All right, so here's a picture. Keep in mind what a function does. A function takes a domain and a target, and specifically the function takes a point in the domain and sends it over to a point in the target. Okay? Point in, point out. That's what functions do. We're going to consider now a different kind of related thing, which is, suppose from that starting point we entertain the idea of changing the input by some amount. So in other words, let's consider that vector at that point, and let's consider then what the corresponding resulting linear estimate of the change in the output is, also some vector. The derivative matrix, what it does is it turns that input change into that output change. Is that cool? So this is just a geometric representation. Why did I take my glasses off? Geometric representation of this formula right there. Input changes to output changes. Is everybody okay with that? Are we all good? All right. Now, again, sweeping formalities aside, let's point out that I could take this equation that we were just looking at, and we can divide both sides by dt. Again, let's not worry about formalities. And that equation then turns into this equation, and I can make an interpretation of that. What I have over here on the left, then, is a velocity. That's time rate of change of position. So that's kind of a change. It's just that it's a rate of change as opposed to a discrete jump kind of a change. So input velocity there, and check it out, output velocity over here. Right, again, it's an instantaneous rate of change, not a discrete change. So another interpretation, you might say, alternative interpretation of what the derivative matrix does. The derivative matrix turns an input velocity into an output velocity. So in other words, if you were momentarily, okay, there's you, that's you right there, and if you were moving at some speed in some direction, if you're moving with some velocity, well, your image would also be moving with some velocity. How would I relate the input velocity to the resulting output velocity? Well, derivative matrix. Everybody good? All right. Okay, now what's the deal with the gradient? Remember, we had an alternative formulation for the case of real valued functions. We had an alternative formulation where we put the gradient there, and of course it was a dot product because vector and vector. Right? So again, real valued functions only, but you can reinterpret the derivative matrix as the gradient, a dot product with the gradient instead of matrix product with the df. So the thing is, we can do all the same little moves. We can turn that into this equation. Note, dot product with the gradient instead of a derivative matrix. And then again, well, there's an output change, there's an input change. Maybe I should view the gradient, not the derivative matrix in this case, as being the derivative. So we kind of seem to have two candidates for the thing that turns input changes to output changes. Is it the gradient or is it the derivative matrix? Which is it? And the answer is it's both. Take your pick. It's morally the same thing anyway. Because if you remember, what is the gradient? The gradient is made up of all of the partials of your function. This is a real valued function. And if you write down the derivative matrix, what is the derivative matrix? Well, there's only one output value, therefore there's only one row, and therefore that one row is all of the partials of your function. Just like the gradient is. So really, writing it as gradient dot, or writing it as df matrix times, the only difference is the sort of the notational choice. The actual numbers involved, the actual terms when you do the dot product with your dx, it's all the same algebra. It's exactly the same. It's just a different sort of notational choice. So anyway, I just like to point that out, that we're not making an arbitrary choice here. They're really the same. So when I say that the derivative matrix is what turns input changes into output changes, well, you can make the exact same statement about dot product with the gradient vector for real valued functions only. Of course, gradients only exist if you're talking about real valued. Okay, is everybody okay with that? All right. Okay, so let's see here. Oh, we're short on time. Let me say a couple of really quick things about section 2.4. I want to make the observation that, of course, we already know this, that the derivative matrix, it's a matrix. Matrices are always linear, so we already knew that. But specifically, keep in mind what df does. df is a function that takes input vectors and gives you output vectors. Now, I want to talk about a easily conflatable idea, but it is in fact very different. And that is, I want to talk not about df, I want to talk about d. D, the act of differentiation, is something that you do to a function, and the result of doing d to that function is that you get a matrix. Right? So we need to distinguish between these two things. There's df that goes from Rn to Rm, then there's d that goes between these, from the abstract vector space of functions into the abstract vector space of matrices. And so I'm going to make now a very substantially different statement. I said here that the derivative matrix is linear. Yeah. Now here's a very different statement. D is also linear. The act of differentiation is linear. And I'm going to let y'all look at this. So in this sense right here, if you do a linear combination of functions, you get the same linear combination of the derivatives. And y'all can read this example right here that here's a couple of functions. Here's their derivatives. You can look at the linear combination function. Here's its derivative. That's just this linear combination of those two given functions. Nothing particularly new has happened yet. And then just confirm by the arithmetic that if you take the linear combination of the derivatives themselves, that's exactly the same as the derivative of the linear combination function itself. And again, so this arithmetic here confirms as we expect. Okay, we gotta call it a day. Y'all have a good one. See you later. Hope everybody enjoys the game on tomorrow. See you later.